The purpose of this video is notes and guided practice on solving two-step equations, both with models and with algebra. This video is intended for pre-AP math students. This is a 7th grade skill, and it is not a skill that 6th grade on-level students are required to know or will be assessed over. We are going to work through these with a similar idea that we worked through the 1 steps. We'll focus on the picture models first, and then we'll use algebra to back that up. We will also continue to check our work using substitution. For the first one, our goals are the same. Our goal is to isolate the variables. The variables are represented with rectangles, and I see that those rectangles are not isolated. There is a lot of constants that are in the way, and so we'll work through the isolation. Our other idea is the same of what we do to one side, we must do to the other to constantly maintain balance or equality. And we will be using inverse operations to guide us through the undoing process. First, in order to get rid of these constants, I would need to remove 7 of them, but that would technically tip the balance. So if I remove 7 there, I must remove 7 from the right-hand side. And then my balance beam has 2 variables balanced with 6. I want to know how much each variable is, not 2 of them. So now I can split into groups. These 3 could be assigned to one variable, and these 3 could be assigned to the other, so that I believe that the value of each variable or each x would be 3. The original equation would be 2x's plus 7 is equal to 13. And I'm thinking it's 3. But now we'll show using algebra what was just showed using a picture model. So the first thing that we did in our picture is we removed 7. Removing is subtracting. I know that adding 7 and subtracting 7 will essentially cancel out and make 0. (13 minus 7 is 6. The next thing that we did in our picture model is we took the 6 and we split it into 2 groups. Splitting is division. If I multiplied by 2 and then divided by 2, these would essentially cancel one another out. That would leave me with only an x. And then 6 divided by 2 is equal to 3. I get the same solution that I got in the picture model. So all I have to do is check my work, and hopefully the solution is in fact 3. I'm going to substitute in the solution, write the equation, think of it like an order of operations problem, and then I'm going to work it forwards again. I have multiplication and I have addition. In the order of operations, multiplication comes first. 2 times 3 is 6. 6 plus 7 is 13. I have 13 on the left, 13 on the right, and so I do have a true statement. as you can see, when you have a two-step equation, the scratch work and the checking becomes much more important because there's more room for error, and the ability to use mental math starts to dwindle a little bit. The first thing that we did is we undid addition. You can hear kitty paws on the floor. Then we undid multiplication. And if you look at the title, solving two-step equations, here's one step that we undid. Here's a second step that we undid. For the second example, I see on the balance beam that I have three variables. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 unshaded or positive or adding constants, balanced with 3, 6, 9, 12, 15. To solve on the picture, first, the variables need to be isolated, and they are not isolated right now. These 9 need to be removed. If I remove 9 from the left-hand side, I must remove 9 from the right-hand side. So the variables are isolated, but I don't want to know how much 3 variables is. 3 variables is balanced with 6. I want to know how much each variable is. Mia, your playing is too loud for a video. Two for that variable, 2 for that variable, 2 for that variable. So I predict that each x is equal to 2. To verify this using algebra, the first thing that we undid was addition. Plus 9 and minus 9 will cancel each other out because they are inverse operations. That would only leave 3 x's. 15 minus 9 is 6. Then we were splitting, which is division, and the opposite of multiplication is division. Six divided by 3 is equal to 2. So I have the same answer using the picture model and the same answer using algebra notation. I'm going to substitute my solution of 2, and then I will work the left side of the equation through again to simplify it and hopefully get 15. First, multiplication, 3 times 2 is 6. Secondly, addition, 6 plus 9 is 15. And I do get a true statement, so I know that the solution of x equals 2 is correct. For the third one, I see 4 x's shaded, which is negative or subtracting. Subtracting a positive is the same thing as adding a negative. 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's equal to 9. To solve using the picture model, I again want to isolate the variables. However, there are 3 shaded squares in the way. I can't simply cross off 3 shaded squares and 3 unshaded squares. Those are not the same. That would not be balanced. Yes, it's crossing off squares, but you have to consider the value of each square. So if I can't cross off, there is another way that I can cancel out negatives. Negatives and positives cancel with one another. So I could actually add 3 on to keep the balance. Add 3 over there. And even though it doesn't look like the variables are isolated because there's more happening in the picture, these values have a net result of 0. So now I see that 4 variables is equal to 12, but I want to know how much each variable is. So I'm going to split these into 4 equal groups, and I would find 3 in each one. 3 for this variable, 3 for this variable, 3, hoping that the value of x is equal to 3. We'll verify that using algebra. The first thing that we did is we undid the subtraction using the inverse operation of addition. We added 3 to each side of our balance beam. And 9 plus 3 equals 12. Next, we took 12 and we split those into 4 equal groups. Splitting is division. Division is also the inverse of multiplication. And then 12 divided by 4 is equal to 3. The kitty is chasing a June bug. She sometimes gets hyper in the morning. These are true stories from Miss Halpern's household. I'm going to take the original equation again, substitute the supposed answer. Sorry, I have to shift the iPad for just a moment. Mia, what are you looking for? Are you looking for a bug? Chubby. You can see the outdoor kitty looking like a statue on the deck. Yeah, we don't want to see your rear. Okay, back to math. To work the equation through forward again, 4 times 3 would equal 12. 12 minus 3 would equal 9. And that's a true statement, so I know that we did it correctly. The final example that we'll look at has a variable that's been cut in half. And I'm just going to show my division using fraction notation because we've already been showing division using fraction notation. The x is divided by 2, it's cut in half, and then we have adding 2 balanced with 5. If I solve using the picture model, I want to isolate the x. I need to remove these 2. What I do to one side, I do to the other side. Then I see that half of an x is balanced with 3, but I want to know how much an entire x is. This half is these 3. The other half would be another 3, meaning the entire x is 6. So I'm going into my algebra work thinking that x should be equal to 6. The first thing that we did is we undid the addition using the inverse of subtraction. Then I took the 3 and I doubled that. This was for one half and this was for the other half. Doubling is multiplying. Also, multiplying by 2 is the inverse of dividing by 2. And 3 times 2 is 6. That's the same solution that we thought it was on the picture. To verify that, my original equation, I will substitute a 6 in the place of x. Order of operations says do division before doing addition. 6 divided by 2 is 3. 3 plus 2 is 5. And I did get a true statement. Going back to the algebra, we undid addition, and then we undid division. So looking at all of our notes, we used picture models because the visuals are always nice when you're faced with something new and challenging, is to connect back to what you know or to look at the situation concretely with something visual. Then what we did in our pictures, we wrote out with correct mathematical algebraic notation using inverses, using the idea of equal treatment or balance to isolate a single variable is the goal. And then we checked our work using substitution, where we took our supposed answers, substituted them back in, and worked through simplifying the left side of the equations again, and we got equal statements. If you didn't have a picture, you might wonder, how do I know what to undo first? There is a pattern that I hope you saw developing. I'll point it out to you right now. Look at the first things that we always undid. We undid adding, adding, subtracting, adding. Then we undid multiplying, 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 dividing. We always undid addition first, or subtraction, and we always undid multiplication or division second, which is the order of operations in reverse. I'm going to make a note on the back of the paper about this, and I'm going to use the first example of 2x plus 7 equals 13. On some homework assignments, you saw little T-charts where you wrote what you were doing to the variable and what would be the plan to undo it using inverse operations. If I do the same process, I'm going to focus on this side of the equation, the left side that has the variable in it. And in my mind, I'm going to run through the order of operations. Do I see any parentheses? No. Do I see any exponents? No. Do I see any multiplication or division? Yes. I see that x is being multiplied by 2. Do I see any addition or subtraction? Yes. I see that 7 is being added to the x. So when we do problems, and when I want to identify what is being done to a variable, I'm going to list these following the order of operations, now that you're looking at multiple steps, not just one step. Then I will make my plan of how to undo these. The inverse of multiplying by 2 is dividing by 2. The inverse of adding 7 is subtracting 7. But when you solve an equation, you are going to undo in reverse. First we subtracted 7, then we divided by 2. First subtract 7, then divide it by 2. Before, I've used the idea of wrapping a gift to be a metaphor for that. And I don't have a gift with me right now, but what I do have nearby is a little packet, a little envelope of, I'm just going to put something inside of it to build a case. So let's say I'm going to wrap up this random photo that I just found in my living room of some ratios. And I'm going to wrap up this photo in a little envelope. The first thing I would have to do is insert that into the envelope. Secondly, I would need to clasp it. So let this be the putting it in the envelope. Secondly, clasp it. If I handed this to a person and I asked them to undo what I just did, they can't remove it from the envelope. They have to work in the reverse order that I worked. They would need to unclasp first, signified by the last thing I did is the first thing they will undo. And then, secondly, remove the item. So go into this with a gift wrapping metaphor. Previous students have referred to the reverse order of operations as SADMEP instead of PEMDAS. When you get into higher level mathematics, there would be exponents and there would be grouping symbols, and you would still do the opposite operation, but those would happen after the fact. You would always undo any addition or subtraction, then you would undo any multiplication or division, then you would undo any exponents, then you would undo any parentheses. So it follows order of operations, but in reverse. Think about the do as wrapping a present, and when you unwrap a present, everything that was done you have to take apart in reverse.